Hello and welcome to this next Year 10 optics video in which we will cover the ideas of total internal reflection. So we're going to have a look at what it is and what can cause it. Here I've got three different images. One showing our normal idea of refraction, where we have an incident ray of light. In this example, we're travelling from an optically dense medium to a less optically dense medium. So my refracted ray actually moves away from the normal. In my second example, we still have the process of refraction, but here the angle of incidence is a little bit larger. And this means that when the ray of light moves away from the normal, it actually moves away at exactly 90 degrees. When this happens, we say that the angle of incidence is actually at the critical angle. The third example I've got is total internal reflection. This is when the incident ray of light enters my optically dense medium, but is unable to refract out to my less optically dense medium. In this case, what happens is the ray has to be reflected inside, and we say this is called total internal reflection. In order for this to happen, my angle of incidence, which is the angle between the normal and my incident ray, has to be greater than the critical angle that we saw in our second example. But I suppose the main question here is actually, how would we even know what the critical angle is? Thankfully, we're able to calculate the critical angle by using quite a simple equation. What we say is that my refractive index, which you should remember from your previous lessons, as being equal to sine of the incident angle divided by sine of the refracted angle, is equal to 1 divided by sine of this critical angle. So if I already know what my refractive index is, then I am able to find what my critical angle could be. In order to do this, I would have to use the inverse function of sine, which hopefully you will have already come across through your work of refractive index. So if we wanted to find the value of the critical angle for any given material where we know the refractive index, we first have to rearrange our equation to find C in terms of the refractive index. So initially we can rearrange this to say that sine of angle C, the critical angle, is equal to 1 divided by n. Then we need to take the inverse function of sine. So we would then say that C is just equal to sine, and we put this little -1 here to show that it's the inverse function, of 1 divided by my refractive index. If we were to approximate the refractive index of air to be 1, why would total internal reflection not be possible? I'll give you a minute to think about this, pause the video and then move on to the final question for you to think about before next lesson. So we've looked at this idea of total internal reflection. I'd like you to think about the following. Would the colour of the light affect the critical angle of a material? In other words, would the critical angle for a red light be different to the critical angle of a blue light? I'd like you to justify your answer.